Welcome back to lecture 7, and this is our 7b, where we're going to look at our volumes of solids of revolution, but now we're revolving them around a line that's not an axis. So again, the picture here is the most important part. So we're going to get our little sketch here. So we're working with y equals square root of x. Sorry, y equals x squared, and y equals x, and we're revolving around y equals 2, okay? So I've got square y equals square root of x. I've got y equals x. Okay, and so we've got this region over here. So I'm going to get rid of this stuff over here. Sorry, what did I drew that wrong? Back, train up. Y equals square root of x goes this way. So what we're really doing, we don't need the negative part. Is we're revolving this area here around the line y equals 2. So y equals 2. First of all, let's find our intersection points. So if I set x squared equal to x, subtract it over, factor, that's going to give me x equals 0 and x equals 1. That gives me this value and this value. So this is 0 and this is 1. And if we plug them back in, we also know that the y value here is 1. So the line y equals 2, and I'm going to adjust my picture here because we actually don't need the negative part. But we are going to revolve that section around the line y equals 2. And the line y equals 2 is going to be up here. So I'm going to flip this area around that section. So that means that this point will translate up here to 3 and 4. And it's going to look something like this. And it's got a big old hole in the middle. Okay, so this is my area again here. Okay, and what happens is that our cross-sectional washer here is going to be something like this. So it's a very thin washer because it's a very thin area. Now, see, the key thing here is that we need the radius. And the radius is going to go from, my inner radius has to go from my line, y equals 2, up to the outer curve. So that's my r outer. And then from 2 to my inner curve, that's my r inner, okay? So what happens to our area curves? So our area is pi times the integral from. We're integrating over the x values from 0 to 1. Now, we are going to think about the area here as top minus bottom for each of these radii because our bottom is now not 0, okay? So we're going to take the curve for RO, right? The curve is the top part here, up all the way up here, and the bottom is the 2. So that area, if we were finding it, would be the curve x squared minus 2. That's our radius, so we're going to square it. Minus the bottom one goes to the line, and the line is y equals x, but we're stopping at 2, so we subtract the bottom of the area, which is 2, and then square it. So that gives us pi times the integral from 0 to 1 of x squared minus 4x plus 4 minus, oh wait, hold on. Let's fix that. No, like that though. My power should be 4 and 2 because I'm squaring a square. Here we're subtracting x squared minus 4x, so plus 4x if you distribute the negative, plus 4, which is minus 4, dx. Let's see what happens here. We've got x to the 4th minus 5x squared plus 4x, and the 4's cancel themselves out. So dx. All right, now antiderivative. 1/5 x to the 5th minus 5/3 x cubed plus 2x evaluated from 0 to 1. When we plug in 1, we get 1/5 minus 5/3 plus 2 minus 0. And that's going to give us, let's see, 1/5 minus 5/3 plus 2. Math fraction gives me 8/15 pi. Okay, and so the main difference here is that when you find your radius, you're going to subtract off that bottom line, wherever that happens to cut things off. Okay. And in the second one, we're going to rotate the same region around x equals -1. So same region. So I want to anticipate where I'm drawing things. All right, so our line of revolution is going to be at x equals -1. And our graph goes from 0 to 1 on both the x's and the y's. And so it's this curve and this one, right? This is our area. And we're rotating it around this line right here. So if this is -1, then my point at 0 will come over here to -2. And the point at 1 will move over to -3. And so it will look something like this. And that's the same area. And we're rotating it around. And so our cross-sectional area, again, is a disk. Sorry, not a disc, a washer. This is a washer. The outside radius goes from our line, whoops, sorry about that, from our line out to the outside of the curve. That's my RO. My inside radius goes from the line of revolution to the inside of the curve. So when I go to find my area, this is pi times the integral from 0 to 1. Now, keep in mind that it's 0 to 1 because now we're revolving the other direction. So notice that my my washer is now horizontal, which means everything's going to be with respect to y. So I want to be thinking about my outside function there is going to be, so we had y equals x squared, which is going to translate to x equals square root of y. Okay. And it's just the positive version because we're only using the first quadrant there. And that's the curve, so that's the yellow one. And then you have the line y equals x, which is just x equals y. And that's what I'm going to draw in blue. So that's this one right here. Okay, so what I'm going to do, we need our outer radius squared. So the outer radius is my curve, which is the outer curve, which is yellow, which is square root of y, minus the line, so minus -1. The inner radius is going to be the line y minus -1. So we get pi times the integral from 0 to 1 of square root of y plus 1 squared minus y plus 1 squared dy. From there, we simplify and get our value. From 0 to 1, this becomes y squared plus 2 square root of y plus 1 minus y squared minus 2y plus 1, but times -1, so minus 1 dy. And we get pi, integral from 0 to 1. Of y squared, actually, let's see what happens here. Y squareds cancel, the 1's cancel, and we're really only integrating 2 root y minus 2y dy. So that makes life a little bit easier. Okay, this is y to the 1/2, so that becomes y to the 3/2 times 2, so 2 times 2/3, 3/2 minus y squared from 0 to 1. Plug in 1 and we get 2 times 2/3, which is 4/3, minus 1. And so we get pi over 3. Right? When you plug in 0, you get 0.